that is the special topics. So in the last class, we have discussed one of the very important CFD technique that one should employ while solving convection diffusion problem, that is the upwinding scheme. So we have discussed what is upwinding scheme and why we require upwinding scheme for the numerical solution of convection and diffusion problems. There we discussed first order upwinding scheme and the consequences of upwinding scheme for the perspective of numerical stability and the convergence of time-dependent convection diffusion problem. So, under the umbrella of special topics, we shall be learning the primary or one of the key method of computational fluid dynamics, that is called the primitive variable method. Primitive variables method, or you can call it primitive variables approach. So why we require this approach? That is one of the important question that one should ask, why we require this approach. So primarily, the primitive variables approach is nothing but the solution of Navier-Stokes equation, that is the solution of fluid flow problems. So through primitive variable approach, one can solve Navier-Stokes equations, that is the momentum equations, to calculate the velocity and pressure distribution for a flow which is happening in any media or which is happening in general case, or maybe any flowing media, incompressible or compressible, whatever may be. One can apply, or one should apply, primitive variable approach for the numerical solutions of Navier-Stokes equations. This is the most powerful method that is being adopted, or that is adopted by all commercially available CFD softwares or CFD packages, whether it is ANSYS Fluent, whether it is COMSOL, CFX, whatever software you come across, all commercial packages employ this method only. This is the method that all the software packages employ, and this is the method through which one can solve a varieties of computational fluid dynamics problem or fluid flow problems involving fluid flow and heat transfer problems through this method. That is called the primitive variables approach or primitive variable method. Historically, this method was first introduced by Harlow and Welch. I think if you remember, in the first class of our computational fluid dynamics session, we have discussed about Harlow and Welch. It was in the year 1962. They introduced this method in 1962, the primitive variables method, for the solution of Navier-Stokes problem, Navier-Stokes equations, and they published a paper in Physics of Fluids journal. This is one of the benchmark paper in computational fluid dynamics technique.
Physics of fluid.
Yes, Physics of Fluids paper journal. That method was introduced, and they published a paper in that journal.
Okay.
So this is one of the very one of the renowned journal, maybe published by American Physical Society. So 1962. This is historical fact about that method. He introduced the method. Later, the method was modified, or there are one of the milestone. Later the method was modified by one of the famous scientists, or you can say famous engineers in this computational fluid dynamics technique or computational fluid dynamics techniques, by Patankar and Spalding. So I think all of you should remember the name of Patankar and Spalding. Subhas V. Patankar and Professor Spalding. They were the pioneer in introducing this primitive variable method after Harlow and Welch for the solution of Navier-Stokes equation. So Patankar and Spalding. Patankar was basically a PhD student of Professor Spalding at University of Cambridge, And then Patankar, after introducing this method to the world, to the community of CFD, he came back and he joined IIT Kanpur as a faculty for a few years. Then he left IIT Kanpur, and then now he is at University of Minnesota, Minneapolis. He is a professor there, full professor. He's one of the famous, and he's one of the benchmark professor in this area of computational fluid dynamics technique. So that numerical fluid flow and heat transfer book that I referred in the first class, if you remember, that book was written by Subhasji Patankar. That is basically called one of the very important book, or you can be Bible of CFD or Bible of computational fluid dynamics for this primitive variable approach. Now, apart from this historical perspective, why we should require this primitive variable approach? If you remember, one can also solve fluid flow problem by stream function vorticity method that already we have learned in the last to last class. The stream function vorticity method. To the stream function vorticity method, one can basically solve a class of fluid flow problems. Now the question is, if the stream function method is there, why we again use this another approach for the solution of Navier-Stokes equation? Can anybody answer this question? Shivnath, why you are solving this? Why you are applying? Why you are going for this primitive variable approach?
Sir, from the stream function vorticity equation, we cannot directly find the pressure
Right.
distribution.
Another. This is fine. Another very important point is there. Already I have discussed in the class. Already I think it is there in the class notes.
Something false something we
No.
use.
False tangent is something different. False tangent, that is something different. It is something called false tangent method, but that is something different. So basically, there is certain limitation. Yeah.
Sir, as we are using stream function, so it is confined to 2D problems only.
That is the answer. Very good. Very good. Basically,
Okay,
stream function vorticity method, we cannot solve three-dimensional problem. If you cannot solve three-dimensional problem, then what is the use of this numerical technique? Because in reality, all the problems are primarily three-dimensional problem. So if you cannot solve three-dimensional problem by using this stream function vorticity method, so there is no point of employing this method for the there is no point of extending this method for the three-dimensional problem. So that is the primary limitation of the stream function vorticity method, that we cannot solve three-dimensional problem with the stream function vorticity method. So there are other limitations also in the stream function vorticity method. We cannot basically specification of vorticity boundary conditions. Specification of vorticity boundary condition is very difficult, and also the stream function boundary condition is okay. It can be generated, or it can be detected from sets of inlet or outlet conditions. But the main problem is the stream function vorticity method. We cannot solve three-dimensional problem. That is one of the very difficult part of stream function vorticity method. So that's why this primitive variable approach was introduced. In this approach, instead of solving the equations, the Navier-Stokes equation in indirect way, it is solved in direct way. That is, it is solved with the primitive variables. That is the variables u, v, w, and phi. So u is the velocity in x direction, v and w are the velocities in y and z direction, and p is the pressure. So directly in this approach, velocities and pressures are solved. This is the primitive variables approach. That's why this primitive variable approach is introduced, and it is now one of the this is the method that is being employed for the solution of fluid flow problems. Again, it is not so straightforward to employ this primitive variable approach, or you can say direct solution of Navier-Stokes problem for this straightforward finite difference grids. That is, if you have finite difference grids, it is not so straightforward to solve this primitive Navier-Stokes equations for this primitive variable with the primitive variable approach. That is, if you have a Navier-Stokes equation, and if you discretize these equations by considering the finite difference method of discretization technique, you will face very difficulties, or if you will face lots of difficulties while solving this primitive variable approach. So in some cases, if you have a certain classes of pressure or velocity distribution in the flow domain, particularly flow domain, you may get wrong solution. That is the primary problem of the primitive variable approach. And approach
So, sir,
or
can you repeat the problem again?
can we what problem?
The problem
Yes.
of primitive variable approach.
Okay. The problem of primitive variable approach I will be discussing anyway. The problem of primitive variable approach is that if we use finite difference way of discretization technique,
Mm-hmm.
you may face lots of difficulties, or sometimes you may get, or you may end up with a wrong solution, wrong numerical solution. If you discretize the governing momentum equations the way one discretize with the finite difference grids, that is the basic problem of primitive variable approach. So let us see what are the problems one may face while discretizing any governing equation with the primitive variable approach. To start with, let us consider one-dimensional steady-state momentum equation. This is a one-dimensional steady-state x momentum equation, right? This is a one-dimensional steady-state x momentum equation means your Navier-Stokes equation, x momentum Navier-Stokes equation. One-dimensional steady-state, no time dependency, only one-directional flow. This is the consideration of Navier-Stokes equation. So what is the equation? So you have a rho u del u del rho del u del t plus rho u del u del x plus rho v del u del y equal to minus del p del x plus mu del 2u del x2 plus del mu del 2u del y2. Since it is a one-dimensional problem, y components are 0, and also this is steady state problem, time dependent component is also 0. So we have only one equation, that is rho u del x equal to minus del p del x plus mu del 2u del x2. This is the one-dimensional steady state momentum equation. Suppose now if you want to discretize this equation with the finite difference way of discretization, suppose this is your finite difference points, point number 1, point number 2, point number 3, so on, point number I, and the distances between the points are delta x. This is the x directional equation, delta x. So please see this is very important. So please understand this with due understand. So due correction, even please try to understand these facts, because this is one of the very important consideration why one cannot directly employ finite difference grids for this primitive variable approach. So please try to understand this. So this is the equation. Now we are discretizing this equation. So let us say this is the equation, and we are discretizing this equation by this finite difference approach. So here we are applying central differencing method. Rho ui del ui plus 1 minus ui minus 1 by 2 delta x equal to minus pi plus 1 minus pi minus 1 by 2 delta x plus mu I. So this is a viscosity. Ui plus 1 minus 2 ui plus ui minus 1, this is delta x square. This is okay? Everybody has understood? Right? Discretion? Is that clear?
Uh,
Yes?
Yeah,
yes,
yes,
sir,
yes.
yes,
FDM method. Central
yes, sir.
difference.
Simply
The central
FDA method we have employed
Central
for a
difference. Yes.
central differences method for this
Yes.
discretion of this momentum equation.
Mm-hmm.
Now let us see, because any flow to happen, what you require. Suppose there is a conduit, and through the conduit you want to flow to happen. So what is the required?
negative pressure
What is
gradient.
the pressure gradient is required, right?
Pressure
One
gradient
must,
is
one must require the pressure gradient.
Mm-hmm.
Now, in any one-dimensional flow situation, suppose you have this OEV pressure gradient. In some point, pressure is 100, another point is 300, next point is 100, another point is 300, next point is 100, another point is 300. So you may have OEV pressure gradient. This is very practical. In practical application, one may face this kind of OEV pressure gradients. Okay. So in practical application, one may face or one may come across this kind of wavy pressure gradient in the flow domain. So if there is a wavy pressure gradient in the flow domain, what will happen? There will be generation of vortices. So that is separate topic. So in general, in fluid mechanics problems, one may come across this kind of wavy pressure gradient in the flow domain, right? Suppose if we have this wavy pressure gradient, then what will happen? What will happen? Can you answer this question, Shodadeep? What will happen if we have wavy pressure gradient?
Mm. The del to del x would not be constant, I think.
That is right. Repetition would not be
Uh,
constant, but what will happen then? Suppose
Del
you
P
have a
del X zero,
wavy.
zero for all values of x.
Yes, that is the right thing. Pressure gradient. See, in a discretized form, discrete equation, you can see pressures are basically not adjacent grid points. There are alternate grid points, right? I
Mhm.
plus 1 and I minus 1. So 300 minus 300. So let us see in the next slide. So pressure, so that is basically you can see you are getting a pressure which is basically from the alternate grid points,
Oh,
right?
pressure gradient will be 0.
Del P del X will be automatically 0,
Oh,
right? If del
Sir,
P del X
then
0, yes, yeah.
the central difference
sir,
method.
then if we
Uh-huh.
don't use the central
Uh-huh.
difference scheme,
We have to use central difference scheme because in the diffusion part, this part you have
Mhm.
used central difference scheme. To make consistency in the scheme, here also you have to use central difference scheme. Okay, okay.
The del to u del x to means other schemes cannot be applied.
You can apply other scheme also. You can apply other schemes
Backward scheme.
also. First order scheme also you can apply. If you
Hmm.
apply first order scheme, you will not get accuracy in the solution. Then again there will be a huge problem in the round of error. Right?
In del to u del x to means the backward difference technique cannot be applied or forward difference. Instead
Forward,
of
forward,
central.
forward difference you can apply, but in the same time, what will happen if we apply forward difference technique?
Yeah.
Then you will come up with a less accurate solution. Solution accuracy will get reduced, and your convergence will also get lost. You also, it will be also lost, and you will also convergence will actually you will not get actually convergence. Finally, your convergence will be lost. I think there is
Um,
some of you have this microphone is on. Some sound is coming. I don't know from whom. Yeah, now it is okay. Yes. What is your question? Shimnath, you were asking something.
no sir.
Uh,
so actually,
so
I was asking my
uh,
actually mother is talking over the phone, so the actually
no, fine, fine,
sound
fine,
was
fine. Okay. No,
coming.
that is fine. Okay. You can. Your question is okay. Now you can mute your microphone. Your question was like, can we use backward difference technique here, forward difference technique here, or backward difference technique? All these three equations, you can use backward difference techniques. So let us apply backward difference techniques. So what will happen at the boundary then? What you will do in the boundary? Suppose in the boundary domain, what will do if we apply backward difference technique? Here, what will happen here? Order of error will be delta x, right? First order error. Backward is first order error, right? If your error order is first order, then what will happen? If you try to solve this equation numerically for this first order error with this kind of zigzag pressure difference, you will get immediately divergence in the solution. Your solution will be immediately diverged once we have the zigzag type of pressure distribution. Understood? You can try this at your home if you want. What you can do, you can employ this u del x, you can discretize this backward difference. Del p del x also backward difference, and del 2 u by del x2 you can also discretize this backward difference. If you can discretize all these three terms with the backward difference technique, and if you want to solve this problem uh, to calculate u at every point of the flow domain where your pressure gradient is checker zigzag type of pressure distribution, then what will happen? Your solution error, convergence error will be blowing up to something like this. You will never get convergence. Your numerical method will not get converged. Is that clear to everybody now? Is that clear? Or do anybody has any question?
Yes, sir.
Yes, sir. Yes, sir.
Now again another question. Also, you may also ask another question, that whether if you apply forward difference,
Hmm.
so will we get the similar kind of thing? Yes, you will get similar kind of problem. You can try. So as a toy problem, you can try at your home. You will see that if you write this code, computer code, and try to solve this problem with this backward difference or forward difference, del u del x, del p del x, and del 2 del x lx2, you will get diverge in the solution. Your solution will never converge. Number one, and sometimes you will get wrong solution. When we have this checkered board of zigzag type of pressure distribution. That's why in this finite difference technique or in CFD technique, it is always advisable to use central differencing in convection and diffusion term. Primarily convection term, you should have central differencing technique. So if you employ central difference technique in convection term, you are bound to employ central differencing in pressure term and the diffusion term to maintain consistencies in the numerical scheme employed for the different partial derivatives. Is that clear to everybody now? Is that clear?
Yes,
Or
sir.
no? Okay. Now you have understood that once we have this zigzag type of pressure distribution, what will happen? You will not obtain, like, your solution will be devoid of any pressure gradient. That is, your numerical solution will not have any pressure gradient term. It will be automatically zero, because pressure grid points are alternate grid points, I plus 1 and I minus 1, I plus 1 and I minus 1. So that is, del p del x will be zero. It means your fluid flow is happening without any pressure gradient. So numerical solution you are doing without any pressure gradient. This is that actually bringing an inconsistency in the numerical scheme. That your numerical you will be getting a completely wrong solution in the numerical scheme. That is the primary problem of your primitive variable approach. Now you have understood, already I have explained that is pi plus 1 minus pi minus delta x, that is 100 minus 100 by 2 delta x equal to 0, and pi plus 1 minus pi minus 1 by 2 delta x, that is 300 minus 300 by 2 delta x equal to 0. That is all the cases. Once we have a zigzag type of pressure distribution, your pressure gradient will be automatically 0, and you will not, that means you are solving a numerical scheme, or you are solving a differential equation, Navier-Stokes equation, where your solution will not feel any pressure gradient. That is, there is no any pressure gradient. There is not any pressure gradient, but you are solving that fluid flow problem. So how it is possible numerically? So you numerically it will not be a realistic solution, and your pressure field will be treated like a uniform pressure field in the momentum equation. There is no pressure field at all. No pressure field at all. That is, del p del x is completely zero. So your flow is happening without any del p del x. Numerically you are solving. That's a completely wrong solution basically you will be facing, right? Now this is the situation for one-dimensional case. So what happens if you try to see the situation for the two-dimensional case, right? We may have a same situation two-dimensional case also. Is that so? So we have discussed for the one-dimensional case. Same thing also may happen for the two-dimensional case also. Like, you may have a pressure gradient something like this: 100, next point 300, then 100, 300, 100, then 10, 30, 10, 30, 30, 10, then 100, 300, 100, 300, 100, 10, 30, 10, 30, 10. So this kind of pressure field is called checkered board pressure field. Checkered board. This kind of pressure field is called checker fold. So in general, in reality, in two-dimensional situation, you may come across this kind of checkerboard pressure field for the 2D flow situation. So when you come across for this type of two-dimensional checkerboard kind of pressure field in a two-dimensional situation, then again you will be obtaining the similar kind of problem. You will end up with the similar kind of situation. That is, you are solving your Navier-Stokes equation or momentum equation where pressure gradient is zero. That means, you may obtain an infinite number of solutions for the same set of problem with this checkerboard of pressure gradient, because your solution will not feel pressure at all, because all the cases your pressure gradient will be automatically zero. So it can see del P del X is automatically zero. So your pressure gradient is automatically zero. So you may basically obtain an infinite number of solution with this pressure gradient checkerboard kind of pressure field distribution, because in all situation your numerical scheme or numerical solution will not incorporate this pressure gradient, because pressure gradient is automatically zero for this special checkerboard type of pressure field or checkerboard type of pressure field distribution for a 2D flow situation. Right. So not only in a two-dimensional case, for the three-dimensional case also, you may end up with this with a numerical solution where your numerical field or your two-dimensional field is devoid of any pressure gradient. So your flow is happening in two-dimensional situation, but there is no pressure gradient. So this kind of pressure field is basically called checkerboard pressure field or checkerboard kind of pressure distribution. And notably, the checkerboard pressure distribution, it was introduced or it was given while explaining this problem with the primitive variable approach by Professor Patankar. So I have also written here Professor Patankar. Basically, he introduced the checkerboard kind of pressure field. So if there is a checkerboard kind of pressure field distribution, then you may obtain a numerical solution, or you may obtain an infinite number of numerical solution by adding a checkerboard pressure field to the momentum equation, which will not feel at all the existence of the pressure in the flow domain. Is that clear to everybody? What do you mean by checkerboard pressure distribution and how?
Yeah.
Sir,
Sir, can you repeat shortly?
sir,
Yes. The second question. I'll repeat.
sir,
Yeah.
sir, yes, sir. In which kind of situation we get this kind of field, the checkerboard field?
Okay. Any other question? Two questions I have got. Any other questions from anybody? Shorodip? No.
No, sir, the same
Okay.
question. How,
Oh,
in which
okay.
situation we encounter the wavy pressure
Okay.
field?
Okay. Let me explain. Okay. So Shivnath was asking that let me explain what situation we may encounter this checkerboard kind of pressure distribution, right? So this is something like this. So checkerboard means one point is high, another point is low. High, low. So if we see pressure gradient, high, low, high, low. For the situation that is one point is 100, another point is 300. One point is 100, another point is 300. Okay. Now, in a flow situation where one can apply some external forcing to create a pulsating flow. Do you know what is pulsating flow?
Yes, sir. Pressure will vary a sine of omega t like that.
Yeah,
Yes,
yes, periodic manner.
periodic
It's
manner.
just
Yes,
sinusoidally.
sinusoidal manner. So in that situation, one may face this type of checkerboard kind of pressure distribution, pulsating flow. Is that clear to everybody? Yes.
Yes, sir.
So pulsating flow situation is one of the situation one may face checkerboard kind of pressure distribution. Pulsating flow is one of the very important type of flow. Biologically, it is very important. So how we swallow our food through our food pipe? Through pulsation only, right? Just think of it. How we swallow our food through our food pipe, through pulsation only.
Yes, sir.
Yes. Can we can just do a thought experiment. How is, or you can go through online literature, online repository also. How we swallow our food through our food pipe. Pulsating situation. It is called pulsating flow situation. So basically, we create through the food pipe. Our biological system is such that it creates a pulsation through the food pipe, and by that action only, food once we swallow the food actually, it goes through the food pipe to the stomach. Understood? Is that clear to everybody?
Okay.
Yes. Okay.
Yes, sir, it's clear.
So if we have a pulsating flow situation, then one may face this kind of checkerboard kind of pressure field. So the question was that, then again I am coming back to the question asked by Sivnath. Then what is, like, again I have to repeat what basically I wanted to mean. So in general, if we have this checkerboard kind of pressure field distribution in a two-dimensional flow situation, what will happen if we perform this pressure gradient? Then the pressure gradient will be automatically 0, del P del X, right? If del P del X 0, so for a particular situation, you are obtaining, or you obtain a solution of Navier-Stokes equation to this primitive variable approach, numerical solution finite difference. Then what will happen? So for the same pressure, your solution will not feel the pressure existence of pressure gradient, right? That means if whether you are adding this checkerboard field of checkerboard kind of pressure field with the Navier-Stokes equation, or whether you are not adding, it does not matter at all, because all the situation, it will pressure field will be automatically 0, right?
Okay, sir.
Okay, so that means you may obtain an infinite number of solution with the checkerboard pressure field distribution. If whether you are adding it or you are not adding it, does not matter to the numerical pressure field distribution. That is the primary problem of this primitive variable approach. When we come across this kind of checkerboard kind of pressure field, or checkerboard kind of velocity distribution, checkerboard kind of velocity distribution, and checkerboard kind of particularly pressure distribution to the flow domain. Again, let us see what is happening to the continuity equation, because continuity has to be satisfied. Any numerical simulation or any flow to happen, continuity has to satisfy, right? Now let us see what is happening to the continuity equation. So if we discretize, this is a one-dimensional continuity equation. So we are discussing about one-dimensional flow situation. So this one-dimensional continuity equation, del u del x equal to 0. So if we discretize this, what will happen? Ui plus 1 minus ui minus 1 by 2 delta x equal to 0. That is ui plus 1 equal to ui minus 1. That means you are getting a OAV pressure field. Ui plus 1 equal to ui minus 1. The pressure field basically is a OAV. They are basically two consecutive. There is no relationship between the two consecutive velocity fields. Velocity is there. Similarly, one velocity is there, again another velocity is there. So these velocities are equal. These velocities are equal. These velocities are equal. So that means you are getting a OAV kind of velocity field, which is not at all realistic to satisfy the equation of continuity in flow domain. That means the same way when you have checkerboard kind of pressure field, your solution is not feeling any pressure, or numerical solution is not feeling any pressure. You are getting an absurd solution. You are getting a wrong solution of the numerical solution of the Navier-Stokes equation. Similarly, once you discretize the continuity equation, we again prove that if we use this similar primitive variable approach with the finite difference kind of methodology, with the checkerboard pressure field or checkerboard or any zigzag pressure field, once you have zigzag kind of pressure field, you will end up with a wavy velocity field in relation to the continuity equation. That means you end up with a velocity wavy kind of velocity field because two consecutive grid points are equal. Basically velocities are equal after one grid point apart. So ui plus 1 equal to ui minus 1. There is no relationship between the velocity field between ui plus 1 and ui. There is no relationship between the velocities ui plus 1 and ui, but there is a relationship between the velocities ui plus 1 and ui minus 1. The one grid point apart, right? That creates basically a wavy kind of velocity field in the flow domain, or that creates a numerical solution which creates a wavy kind of velocity field, or that yields a wavy kind of velocity field, or solution is basically a wavy kind of velocity field, which is not at all realistic. In some cases it provides a wrong solution. Your solution will not get converged. So this is the one of the primary problem. Have you understood this continuity equation aspects? Similar to the pressure equation that already I have explained. Is that clear to everybody? Yes?
Yes, sir.
Okay. Okay, so since it is clear, that means you may end up with the wavy kind of velocity field to the flow domain. Your numerical solution will be the wavy kind of velocity field. It will show a wavy kind of velocity field. That is not at all realistic, and some cases your solution may not converge. So this is particularly, there is one technical term that is called pressure velocity decoupling. That is called pressure velocity decoupling. So there is no relationship between pressure and velocity. Velocity and pressure are decoupled, and it is not happening because pressure field is becoming zero and pressure field is getting decoupled from the velocity field. So that is called, in CFD technique or in the CFD terminology, it is called pressure velocity decoupling. Understood? Please remember this technical term. It is called pressure velocity decoupling. Is that clear to everybody? What do you mean by pressure velocity decoupling? Is it clear?
Yes, sir.
Okay, so in the primitive variable map approach, which is one of the most important approach for the CFD technique, if we use finite difference grid, that is all the grid points, velocity grid point and pressure grid point are at same pace, the same location, you may face the problem of pressure velocity decoupling. Okay, so when you are facing this problem, when your grid points, pressure grid points and velocity grid points are at the same location, you may face the problem of pressure velocity decoupling in the numerical solution of the problem. Now you may face the problem of pressure velocity decoupling to the numerical solution of the problem. So you need to resolve this issue. The remedy, how to resolve this issue, basically, that means let us explain in a much more clear fashion how to resolve this issue. That means in a finite difference method, these are your grid points, right? These are your grid points. So in these grid points, basically you are specifying u, you are specifying v, and you are specifying p, right? All the primitive variables u, v, and p, all the primitive variables are specified at the same grid points. Okay, all the primitive variables are specified at the same grid point, and that is creating a problem is called the pressure velocity decoupling. Pressure velocity decoupling. Okay, then what will be the possible remedy? What will be the possible remedy? This is creating pressure velocity decoupling. This problem is that is creating this problem, pressure velocity decoupling. So what is the possible remedy? How we can avoid this pressure velocity decoupling? Can anybody answer this question? Shorodip, how we can avoid?
Sir, I don't know.
Okay. Any idea, Shivnath?
No, sir.
Okay. It can be avoided if we specify U, V, and P at different grid points. Is that clear? Instead of specifying U, V, P at the same grid point, we can specify in a finite volume cell. In a finite volume cell, we can specify the primitive variables U, V, P in a different grid points. That is called the staggered grid. That is basically called or the staggered grid. Staggered grid. Staggered grid. So this is the remedy that was introduced by Patankar and Spalding, that instead of specifying velocities and pressure at the same grid point, we are not specifying a velocity and pressure at the same grid point. Rather, we are velocity specifying in a particular cell. We are specifying velocity and pressure in different grid points. How? Let us explain it here. That is, suppose you have a, this is very difficult actually using paint. Suppose your two-dimensional domain, please understand this. Two-dimensional domain, you are discretizing this equation, number of finite volume cells. So these are basically a particular cell. So why you would be doing? You would be specifying. Suppose these are your pressure grid points. Suppose these are the cells, grid points. These are the grid points. These are the grid points. Grid points. So in a particular cell, so because cell, in a particular cell, this is a cell. So this is your cell of your finite difference or finite difference method. Instead of specifying all the velocities and pressure at a particular grid point here, what you will be doing, you are not specifying all the velocity and pressure at a particular grid point. What you will be doing, you are specifying pressure at the center of the cell, velocity at the face of the cell. So it will be x directional velocity u face, and y directional velocity will be v. So your indices, it will be pij, u will be ui plus half j, and v will be vi j plus half. So velocities are specified at the faces of the cell, pressure is specified at the center of the cell. This is a remedy, and this type of grid is called staggered grid. Staggered grid. Is that clear to everybody? I think you may have many doubts, so please ask me if you have any questions. This is a very important technique. This is one of the important technique used in computational fluid dynamics.
Sir, if the situation is not like the checkerboard problem, then if we use the solution as we used before, so will there be any problem in that case?
Yes, there will be a problem. You can try it at home. If there is a situation of there is no situation of checkerboard kind of situation, if your flow velocity, if you solve your Navier-Stokes equation without employing this staggered grid, what will happen? You may get divergence in a numerical solution. Your solution may be wrong in some cases, or you may get very poor convergence. For high Reynolds number flow, you may not at all solve your problem at all. You may not get the solution for high Reynolds for flow at all. So those are the problems you may face for the high Reynolds number flow or moderate range of Reynolds number flow. Understood?
Yes, sir.
That is the one of the critical question of fluid mechanics. In fluid mechanics, if you want to solve fluid flow problem, if you don't use this staggered grid or this kind of technique, simple technique, you may not get your numerical solution at all. Your solution will be completely diverse. That was the same question that I also had, that if you don't use staggered grid, then what will happen? I tried it actually. I found that I didn't get any numerical solution of the problem that I was trying to solve.
Okay, sir. Thank you.
Okay, this is the method that one must apply for the numerical solution of Navier-Stokes equation for the fluid flow problem. There's a staggered grid approach. So anybody has any questions on staggered grid? Everybody understood staggered grid?
Sir, if this orientation is changed, there's if the pressure is not at the center or like
Yes.
that, will there be any problem in that case also?
I do not know. It was introduced such that pressure will be at the cell center, velocity will be at the cell faces.
Okay, sir.
Okay, I do not have, because it was introduced in that way only. That's why it is called staggered grid. Velocities and pressures are not specified at the same point. They are specified at different points in the same cell. In the same cell, pressure is specified at the cell center, velocities are specified at the cell faces. Clear? Any question? I am expecting more questions from you people. Any other question?
Sir, why not give the value for pressure for one cell and velocity for another cell? We don't have to go to that UI plus half notation.
Velocity? No, that you can do. No, that means no. Because although that is right. So although basically this is your cell, right? Staggered grid basically what is basically in that finite difference concept, you have a point concept. One point to another point you are moving, right? One point to another point you are moving. In the staggered grid, the cell concept, you have to consider a particular cell.
Okay.
Cell. So this cell is a grid point. You can say grid cell. In the same cell, center is the pressure, faces are your velocity. Okay. Let us say in your home assignment problem, there also you can try staggered grid if you want. But since there is no velocity, it will not be there is no point of the home assignment problem. Basically, what you did, you divided it in a number of grid points, right?
Yes,
Number of grid points. So this is the number of grid points. But here, what you have to do, this is a finite difference method. Straight grid like FDM grids, finite difference method grids. When it's staggered grid, so suppose there is a fluid flow problem. Suppose there is a fluid is flowing here and is going here and it is going here. So in that case, you don't have to. You may not. I think you should not consider in that way. In that case, if you want to discretize this problem, you have to consider cell wise. This is one cell. So you are moving from one cell to another cell. Cell number 2, cell number 3, and cell number 3. So in the one cell, your grid is at the center, cell center is a pressure grid, and cell faces are your velocity. Vertical velocity, this is the horizontal velocity. U and V.
Okay.
Okay.
Yes, sir.
So this is a method.
So I'll repeat the explanation once again. Means the is assignment.
No, assignment problem. What you did, you discretized. What you did, you discretized the domain number of grid points, right?
Yes.
Right. Suppose there is a fluid flow problem. Suppose this fluid is flowing, because in that case it was a heat transfer problem.
Heat
There is no
transfer
fluid flow
problem.
involved. There is no fluid flow involved. So staggered gate consideration may not be applicable, because it may not consider staggered gate, because it's a heat transfer problem. No fluid flow or pressure gradient is there. Suppose you are solving a problem which involves a fluid flow problem. Okay. So in that case, you have to consider cell wise. So this is your cell. This is your discretizing the domain number of cells. So at the cell center are your pressure, and cell faces are your velocities. Okay.
Hmm. Hmm. Okay.
So this is a staggered grid problem. So with this staggered grid approach, this pressure velocity decoupling can be minimized, or there will not be any issue with the pressure velocity decoupling. So if you discretize the governing equation, that's why I have written here. This is a velocity cells, velocity faces, and cell center are your pressure. So if you discretize your governing equation with respect to these staggered grids, basically velocities are specified at the cell faces and pressure are specified at the cell centers, you will not face those kind of zero pressure gradient when there is an existence of checkerboard kind of pressure distribution or zigzag kind of pressure distribution in the flow domain. That's why this is a remedy for the Navier-Stokes equation involving checkerboard, or in general in the primitive variable approach one must use staggered code technique, or this is the technique one should use, or this is a technique which is used for the primitive variable approach for the solution of Navier-Stokes equation in 2-dimensional or 3-dimensional or maybe 1-dimensional problem also. This is the staggered technique. So what are the advantages? Advantages already have discussed. So here you will not face any such problem of pressure velocity decoupling, which is arising out of this checkerboard or a zigzag kind of pressure distribution. There is zero pressure gradient which will be prevailing in the numerical solution of the Navier-Stokes equation. That problem will definitely will not come, and one can obtain very accurate solution for the fluid flow problem with the staggered gate approach, or with this approach only one can obtain varieties of fluid flow solution, whether it is compressible flow, whether it is incompressible flow, whether it is non-Newtonian fluid flow, whether it is fluid flow with heat transfer. All the situation one can obtain this solution with this staggered gate approach or staggered gate technique with the primitive variable approach. And there are certain disadvantages. Advantages are so high, so one can neglect the disadvantage. Disadvantage is basically writing a computational code may be challenging. It is not so straightforward, but it is not also so difficult. It can be written if you perform some thought experiment. If you give it time, already people have written 2-dimensional heat conduction problem. So same thing also you can repeat it with the fluid flow with the staggered gate approach. It is not so difficult also. So that is one thing. Another thing, actually, some interpolations are required in the staggered grid. So that interpolation may require computational extensiveness due to the interpolation of velocity at different grid points. But more or less, this is a technique that is used for this primitive variable approach for the solution of Navier-Stokes equation for the fluid flow and coupled fluid flow heat transfer problems. Any questions up to this?
Yes, sir. Sir, how do you write the discretized equation for the staggered grid approach?
Can you try by yourself?
Yes, sir. I instead of
you try it. Show it to me. You try it.
Okay, sir.
Okay, try it. It will be very interesting. Try it.
Okay.
Say consider 2-dimensional Navier-Stokes equation. You try it and see how it is coming. Okay, then we can discuss.
Okay, sir.
Okay, so now let us come to the fundamental building block of CFD technique with the staggered grid. It was introduced by Professor Patankar and Spalding with the staggered grid approach. He introduced this method in 1972. This method is called simple method. The full form is semi-implicit method for pressure linked equations. Please remember, this method is called semi-implicit method for pressure linked equation, which is termed as simple algorithm. It was introduced by Patankar and Spalding in 1972, and this method is called semi-implicit method for pressure linked equation. The algorithm is called the semi-implicit method for pressure linked equation. So, if you want to solve Navier-Stokes equations numerically for two-dimensional and three-dimensional problems, you have to apply this method, simple method or semi-implicit method for pressure linked equation for the numerical solutions for Navier-Stokes equations. So apart from the simple method, there is another method is also there. It is called marker and cell method. It is not in the scope of its syllabus, but this is widely accepted method. It is widely used for all the commercial packages. You can see at your home, if you open Fluent and ANSYS Fluent, you will be seeing that which method you will be using, simple method. So there is simple method which is widely used for all the commercial packages for all the numerical solutions for computational problems, which one in heat transfer problems. This is a simple method. It is termed as the semi-implicit method for the pressure link equation. So how it is solved? What is the algorithm? I can say in a nutshell. I can give you one example how what is the method. So this method involves basically you need to solve Navier-Stokes equation. So this method involves predictor character step. So that is called prediction and correction. That means you need to first predict the velocity. Once you predict the velocity, then you obtain the solution of predicted velocity numerically. After that, you correct the velocity and also the pressure by satisfying the continuity. This is the gist of the method. So what is that method? That means it depends upon the predictor character approach. So let me explain it here. Simple method, which is called the semi-implicit method for the pressure linked equation, it involves predictor character approach. It's called predictor character approach. That means in the first step, you predict the velocity. You predict the velocity by numerically solving Navier-Stokes equation, governing equation. Then the second step, you correct the velocity by satisfying continuity equation. Okay, understood? Is that clear to everybody? Any question?
Sir, in the second step, we need to correct the velocity.
I'll come to that. Any question up to this? Any question up to this?
No, sir.
Okay. So this method involves a cyclic technique, or you can say guess, or you can say predictor character method. In the first step, you need to predict the velocity by numerically solving the governing equations. Once you obtain the predicted velocity by numerically solving the governing equation, you correct the velocity by satisfying the continuity. Correct? You correct the velocity by satisfying the continuity. Okay, this is basically called the predictor character approach or predictor character method. Let us see what is this predictor and character method. Just a minute. Okay. So the simple algorithm of Patankar So with the predictor step, basically we predict the velocity. Okay, so let us say this is your x momentum equation. Please see this carefully. Please understand this technique with due diligence, because this is one of the fundamental building block of CFD. This is a Navier-Stokes equation. Okay, this is the x momentum equation. Is that correct?
Yes, sir.
Now, in the predictor step, what we are doing, so let us, I'm not writing the detailed discretization part, I'm writing simply one pseudo discretization part. So in a predictor step, what I'm doing, I'm writing del u del t as u star minus up by delta t plus this will be at p plus 1 level, that is this or implicit method, p plus 1 level equal to minus 1 by rho del p star. So we are taking a guess value of pressure. Initially all the values are chosen to be 0. So guess value of pressure, which is p star, del p star by del x, p plus 1 plus nu del 2u by del x2 plus del 2u by del y2 p plus 1. These are all are p plus 1. This is implicit method. That is all is called basically semi implicit method. So we are writing u star. Let me finish. U star minus up by delta t plus this p plus 1 level minus del p star by del x p plus 1 level nu del 2 e by del x2 plus del 2 e by del x2 y2 p plus 1 level. So u star basically your predicted velocity. You are predicting this velocity u star with this guess value of pressure. You are solving this equation iteratively till convergence. Any question on equation number 1?
Sir, by P you mean the Pth iteration?
P.
No. You have not studied the implicit method, explicit method.
Sir, P
Oh,
means
yes, sir.
What is that?
present, sir. Present. P means present,
Yes,
and P plus
yes.
1 means
Present time. Huh.
Present time. Present p plus 1 is present time. Implicit method. Any question on this equation number 1? Anybody has
No,
any
sir.
question?
No, sir.
Is that clear? Understood?
Yes, sir.
Is it understood? So basically
Yes,
what
sir.
you are doing, you can do it, right? So u star minus up by delta t equal to u del u. So I'm not describing this part. So I'm writing in this form p plus 1 level, present time step level, del p star by del p x p plus 1 level, and this also p plus 1 level. So this predicted velocity u star, which is basically predicted velocity. You are predicting this velocity, u velocity. You are predicting this u velocity with the gauge value of pressure, P star. With the gauge value of pressure, you are predicting this u velocity. You are solving this equation till convergence. So now you have obtained your u star value from this equation number 1. Now again we have a y momentum equation. In the y momentum equation also, you can write this equation as v star minus vp by delta t plus u del v del x plus v del v del y p plus 1. Similar, same thing. 1 by rho del p star by del y p plus 1 plus nu del 2 v by del x2 plus del 2 v by del y2 p plus 1. Right? You can write v momentum equation also. Clear? So here u star and v star are your predicted velocity, and p star is basically your guess pressure. Is that clear to everybody? Question number 1 and question number 2, how I have written?
Yes, sir.
Very simple. From common sense, you can write these equations. So these are your predicted velocity. In the predicted step number 1, you have written your own code, and you have calculated your predicted velocity u star and v star for all the grid points. U star basically at a cell phase, and P star basically your guess pressure, which is basically you have initially guessed as a cell centers, and you have obtained U star and V star at all the grid points, predicted velocities U star and V star, and also you have from the guess pressure. So initially you have guessed the pressure. In general, in computational technique, pressure field has to be taken 0 value. Guess pressure generally takes one may take 0 value for faster convergence. So with the guess value of pressure field, you just predict the velocity for these equations. Now you have predicted the velocity. Now what you have to do? You have to correct it, right? Right? Is that so?
Yes, sir.
because it is your predicted velocity. You have to correct it. Let us go for correction. How you can correct it? Let us go for correction. Now, your Navier-Stokes equation, that is your x momentum equation, del u del t plus u del v del x plus v del u del y equal to 1 by rho del p del x plus. So here this is u star your predicted velocity, right? In actual, it will be u p plus 1, right? In actual case, it will be your u p plus 1.
Yes, sir.
Yes. In the corrected step, actually it is u p plus 1. So I am writing it u p plus 1 minus u p by delta t divided by, in actual case, it will be your actual pressure P, but here you have taken gas pressure. In actual case, it will be actual pressure P. So 1 by rho del P del X P plus 1, same thing. Similarly for V, predicted step it was V star. In actual pressure, actual case, it will be your V P plus 1. And your predicted gas velocity pressure is P star, but in actual case, it will be P. So you can, I am writing these two equations as like this, equation number 3 and 4. Any doubt on this equation number 3 and 4? Please let me know. Any doubt? Anybody has any doubt?
So what is meant by the actual pressure? We don't know the pressure beforehand. We have to
No,
take
no,
the
no,
gas
no.
value.
I am basically deriving the corrected step equations, but ideally it should be like this, right?
Yes, sir.
Ideal. These are the ideal equations. This is your gas equations, but your this is ideally it should be like this.
Okay.
Right? Understood?
Okay.
So ideally it should be like this. Ideally, it should not be U star. It should be U. Ideally, it should not be P star. It should not be P star. It should be P. That's why I'm writing this equation number 1 as equation number 3, equation number 2 as equation number 4. Now it is clear?
Yes, sir.
Now what we are doing, let us subtract equation number 3 by equation number 1. 3 minus 1, that is I am subtracting equation number 3 with equation number 1 and subtracting equation number 4 with equation number
2.
2. If we subtract, what will happen? Let us see equation number 3 what is happening. So it will be u plus 1 minus u star by delta t, u plus u star u plus delta t, so it will be cancels out, equal to minus 1 by rho del p del plus 1 plus 1 by rho del p del star 1 it will be there. All other terms will be cancels out, right? This will be cancels out, right? This will cancel out. This term will cancel out. This term will cancel out. Only up star up plus 1 minus u star by delta t, it will be there. This term will cancel out, and this term will be there, minus 1 by rho del p del x p plus 1, and this term also will be there, del p star by del x p plus 1. Clear? Fine.
Okay, sir.
Now I can write this equation as minus 1 by rho del x of p minus p star. So it will be at p plus 1 level. I can write this as right?
Different dependent pressure.
Right. Can I write this equation as this?
Yes.
So what does it indicate? What does it indicate? P star minus P? P minus P star?
Error.
Sir, the actual value minus the
Guess value.
The error.
Error means
Sir.
correction. Right, you are right. It is called error, but it is in CFD technique, it is called the correction. So basically, we need a correction in the pressure. So let us define P minus P star, basically, which is the correction in the pressure, which will require as P prime. We can write this equation as minus 1 by rho del P prime by del x, where P prime is equal to P minus P star, which is basically the correction in the pressure is required, or error in the pressure is required. Right? Once P star is P prime is closer to 0, then you have P equal to P star. Is that clear?
Okay, sir. That means the P star will converge to P.
Exactly, P star will converge to P. Your P prime is the correction that you will require to the P star to obtain an actual pressure P. Clear?
P start. Okay, P prime is the del P prime is a correction. Okay.
P prime is the correction. P prime is the correction.
Oh, sorry. P prime is a correction. Okay, yes, yeah. P prime is a correction.
Clear. Now, so that is 1 by rho del P prime by del x P plus 1 level. Again, it is P plus present time level. So you can write this as UP plus 1 equal to U star minus. So I'm simply doing algebraic calculation. UP plus 1 equal to U star minus del T by rho del P prime by del x P plus 1. Okay. This equation is clear.
Hmm.
So this is, let us say equation number, this is equation number 5. Now if we take derivative of it, so del u P plus 1 by del x, it will be del U star by del x 1 by delta T by rho del 2 P by P prime by del x to 2. This is okay.
Yes, sir.
So I have taken derivative of this equation. Del u by del x P plus 1 equal to del U star by del x minus delta T by rho del 2 P prime by del x 2 P plus 1 level. Okay.
Hmm.
Similarly, also by 4 minus 2, if we subtract equation number 4, equation number 2 with equation number 4, what we will get? Vp plus 1 minus v star by delta t equal to same 1 by rho del p by del y p plus 1 minus 1 by rho del p star by del y p plus 1. That is 1 by rho del y by p minus p star p plus 1. That is 1 by rho del 1 by rho del p prime by del y p plus 1. Okay. That is Vp plus 1 equal to V star minus del T by rho del P prime by del Y P plus 1. Fine. Same thing. What we have done for equation number 5, same thing we have obtained for equation number 6, 7. Same thing, V momentum equation. From V momentum we have from V correction. That means if we take derivative of it del V prime by del Y, so we get del V star by del Y equal to minus del T by rho del 2 P prime by del Y 2 P plus 1. Fine. We are obtaining by taking the derivative. Let us take del y by Vp plus 1. It will be del y by Vp plus 1 equal to del V star by del y, or delta 2 by rho del 2 P prime by del y 2 P plus 1. Okay. Let us say this is equation number 8 and this is equation number 6. Is that clear? Any questions? So again, I have written here that P prime basically P minus P star, which is basically a pressure correction. Is there any doubt up to this? Any doubt up to this?
So last step. So the last step comes from where? Del B. Okay, the differentiating. Okay.
Simply differentiating this equation.
Partial differentiation. Yes.
Any question up to this?
This P dash is equal to P minus P star pressure correction. Yes. Okay.
Any question?
So this gauge value of P star, we have to define them for every value of the for every cell.
Gauge value of
P star.
Yeah, it will be 0. Initially, it is 0 actually. All the cells you have to define as 0 value.
Initially, means initially at t is equal to 0, it will be 0.
Yes, at
Gauge
t equal to 0, it is 0. Yes, gauge value is 0.
Gauge value is 0. Okay.
Okay. Now we have obtained these equations. So I have not written here. These equations are called velocity correction equation. Equation number 5 and equation number 6, you can write it to a hand note. So equation number 5 and equation number 6, 7 are called the velocity correction equation. I have not written here. You can write it at your class notes. So equation number 5 and equation number 6 are called the velocity correction equation, as introduced by Pottenkar. Equation number 5 and equation number 6 are called velocity correction equation. Now let us go back to our continuity equation. What is the continuity equation? Del u del x plus del v del y equal to 0. Right? Right?
Yes, sir. Yes, sir.
This is the continuity equation. Del u del x plus del p del y equal to 0. So at present level, I am writing del u del x p plus 1 plus del u del p del y p plus 1 equal to 0. This is the continuity equation. So what is del u del x p plus 1? Del u star by del x minus delta t by rho del 2 p prime by del x2. Okay. And what is del p del y p plus 1? Basically, I am substituting equation number 6 and equation number 8 and equation number 9. What is del p del y p plus 1? This in del p star by del y equal to minus del t by rho. What happens? Let us see what happens. So, equal to del u star by del x minus delta t by rho del 2 p prime by del x2, which is basically del u del x p plus 1, that already we have obtained from equation number 6, and del p del y p plus 1 is equal to del b star by del y minus del t by rho del 2 p prime by del y 2 p plus 1, that already we have got from equation number 8. Basically, we are substituting the equation number 6 and equation number 8 in equation number 9, which is basically the continuity equation. So any flow to happen, one must satisfy the continuity equation. Without satisfying the continuity equation, flow is not possible, right? That's why we need to continuously satisfying the continuity while solving the problem numerically. This is the one of the important consideration of the simple algorithm. So here, we are basically substituting the expression 6 and 8, equation number 9. So let us see what is happening. So del u star by del x plus del b star by del y equal to delta t by rho. So 1 minus sign is coming. Okay. So what is there? That is del u star by del x plus del v star by del y equal to delta t by rho. Delta t by rho, I am taking this term and this term in the right hand side of the equation. Del 2 p prime by del y2 plus del t by rho del 2 p prime by del x2 p plus 1 p plus 1. So if I write this equations as, you can write this equation as del 2 p prime by del x2 p plus 1 plus del 2 p prime by del y2 p plus 1 equal to rho by delta t.
Hello, sir.
Yes.
Oh, sir, can you repeat the last few seconds? Actually, your sound was
disconnecting, right? Disconnecting.
disconnecting.
Okay. So can you understand this equation, continuity equation? Is that clear? Continuity equation is clear to everybody? Continuity equation?
Yes, sir.
So
Yes,
what we are doing, we are substituting del u star by del u del x p plus 1 from equation number 6, del u del x p plus 1, and del v del y p plus 1 from equation number 8 to equation number 9. So we are writing del u del x p plus 1 as this from equation number 6, and del u del v del y p plus 1 as this from equation number 8. That already we have obtained. Is that clear? Okay. That means del u star by del x plus del v star by del y equal to delta t by rho del 2 p prime del y to p plus 1 plus del t by rho del 2 p prime by del x to p plus 1. Is that clear? Okay. Yes or no?
Yes, sir.
So del 2 p prime del x to p plus 1 plus del 2 p prime del y to p plus 1 equal to rho by delta t del u star by del x plus del v star by del y. Any doubt up to this? Any doubt? Anybody has any doubt?
No, sir.
So actually, I forgot why in the continuity equation it's p plus 1. Why it's not p only?
Why?
Why it's not p only?
Yeah, continuity equation should be satisfying. Actually, one should satisfy the continuity equation continuously while solving the governing equations. So that is called continuously satisfying the continuity. So in order to continuously satisfy the continuity equations has to be set at p plus 1 level. Now it is clear?
Means at every instant you have to satisfy. Hello, sir.
Solution is not also possible. Clear?
Hello, sir. Actually, sir, again your voice was disconnected.
Okay. Let me again. I am explaining. That means why continuity equation is not at P level, right? That was the question.
Mhm.
Now, in numerical solution, you need to continuously satisfying the continuity. The continuity equation has to be satisfied continuously.
Okay.
Okay. So that means when you are solving the momentum equation at the p plus 1 level, you need to solve the continuity equation at the p plus 1 level only. Also, the continuity has to be continuously satisfying. Otherwise, without satisfying the continuity, flow is not possible. Right? For the flow to happen, continuity must be satisfied. Without satisfying the continuity, flow is not possible. Similarly, without satisfying the continuity, numerical solution is not possible. So you need to solve numerical solution for the fluid flow problem is not possible. That means you need to always satisfy the continuity while solving the governing equation. Continuity has to be continuously satisfying. In
Okay,
order,
sir.
in order to continuously satisfy the continuity, you have to solve the governing equation. Continuity equation is the heart of the fluid flow problem. Continuity equation has to be satisfied. Clear now?
Okay.
Yes, sir. Clear.
Now that's why continuity equation is set at the p plus 1 level. Now it is clear. So we have set the continuity equation at the p plus 1 level. Now it is clear how we are getting this equation. Del 2 p prime by del x2 plus del 2 p prime by del y2, p plus 1 p plus 1 equal rho by del t, del u star by del x plus del v star by del y. Is that clear?
Yes, sir.
That's so we can write this equation as grad square p prime p plus 1 equal to rho by delta t divergent of u star vector. We can write this equation as like this vectorial form.
Yes, sir.
Yeah, right?
Poisson's equation.
Right? Can you write this
Poisson is
equation or not? So what is this equation? This equation is called the pressure correction equation or Poisson equation for the pressure correction.
Okay.
Okay. So in the simple, so that means if you can solve this pressure correction equation, once you solve the pressure correction equation, because you know the u star, right? You know the u star, you know u star, you know u star from this equation number 1 and equation number 2 for numerical solutions, right? You know u star. Once you know u star, you can solve this pressure correction equation. Pressure correction p prime. Because u star is known. Clear? Or any doubt?
No, sir.
Clear, sir.
You know u star. Already u star is known from the predictor step. In the corrector step, you're correcting the pressure correction because you're solving the pressure correction equation. This equation has to be solved. Once you solve the pressure correction equation, you will obtain p prime. Once you obtain the p prime, you can calculate p because p equal to p prime plus p star. P star is already known. Then once you know the p prime, you can calculate v, that is actual velocity, v and u because u star is known, p prime is known. This way you have to keep on iterating your loop till convergence. Is that clear now?
Sir, could you please explain the last part you explained?
Okay. Anyway, I will be explaining the last class tomorrow. That is on Saturday, last class of the CFD. But again, I am explaining it. So, so that means what we are doing. You have obtained the pressure correction equation, right? Yes or no?
Yes, sir.
So, in the first step, predictor step, you have obtained u star and v star, right?
Okay, sir.
Yes. U star, v star, you know. Once you know the u star and v star, you can solve this equation 10 because this right hand side is known, only this side is unknown. P prime can be obtained numerically because this is known. P prime can be obtained. Clear?
Okay, sir.
Once you know the P prime, okay, let me write it in a different way so that it will be clear to you. So in the predictor step, you have obtained U star and V star. Right? This is known. Also P star.
Mm. Yes, sir. Then we have to put the U star and V star in the pressure correction equation.
Yeah. In the character step, del to P prime equal to rho by delta T divergent of U star. This is known. So now you can obtain the P prime. Right? The P prime is also known. Yes?
Yes, sir.
Once you know the P prime, then you can calculate the pressure. Pressure is basically nothing but P star plus P prime. Okay? So you can obtain the pressure. Similarly, you can also calculate the velocities, which is your character velocity correction equation, which is that U star is known, P prime is also known. You can calculate UP plus 1. That is current time step value of pressure, velocity. P plus 1, character velocity, UP plus 1 and VP plus 1. Clear?
Okay, sir. Clear now.
This is the simple algorithm, which involves the predictor character step. In the predictor step, we calculate the predicted velocity U star and V star. In the character step, we primarily or we basically solve this equation only, pressure correction equation. This is one of the most important equation in simple algorithm. This pressure correction equation we solve to obtain the value of P prime. Once we obtain the value of P prime, we correct the pressure. We obtain the corrected pressure P equal to P prime plus P star. Then we correct the velocity. U velocity is called velocity correction equation. UP plus 1 equal to U star is known, P prime is known. Or we correct the velocity, P plus 1 and VP plus 1. Basically, we are obtaining the present step time step velocities, UP plus 1 and VP plus 1. This is a simple algorithm or semi-implicit method for the pressure linked equation. Okay?
So
Clear?
P. Okay.
Uh-huh. Any
P
question?
plus
Yes, Simna?
means P is a present. P plus 1 is the next times future
No,
times.
P plus 1 is the present time step. P is the old time step.
Okay. Yes.
I have already explained the class.
Mhm.
You see, just see your class notes, it is there.
Mhm.
Okay, so I'm just stopping the presentation. I'm stopping the recording now. So the last class